Welcome to Deep Dive Ortho, the show dedicated to charting the relentless evolution of medicine and technology. Today, we're embarking on a pretty ambitious exploration. It's a journey that stretches from the foundational achievement of surgical safety right back in the 19th century, all the way up to the frontiers of autonomous operating systems and personalized bionics. Our mission today is explicitly tailored for you, the mid to senior medical professional. We're here to distill the latest in surgical robotics, sensory systems, and the profound shifts transforming orthopedics. We want to give you that precise technical framework to understand what's driving the next generation of patient outcomes. Okay, let's unpack this.
It is indeed a fascinating and, well, a vast scope. When you really examine the trajectory of modern surgery, you can see it's defined by two parallel revolutions that underpin everything we do today. The first, historically, was the foundational achievement of just making surgery survivable by preventing infection. The second, which we are living through right now, is this tireless pursuit of technological perfection and minimal invasiveness.
And what's interesting is that the core motivation, the why, has never really changed, has it?
Not at all. Whether it was Joseph Lister's brave introduction of antisepsis over 150 years ago, or the development of a future AI control system, the fundamental goal is always the same: to enhance patient safety and maximize efficacy. We'll spend our time connecting the dots between that pivotal historical moment and the hypermodern digital systems that are now redefining the physical possibilities in our field.
It's so crucial to appreciate how recently surgical safety was actually achieved. When we discuss these multi-million-pound robotic platforms, we often forget that none of that complexity is even viable without that first historical pivot point. I'm talking about Joseph Lister's work on antisepsis. Can you paint us a detailed picture of the surgical environment before his intervention? What were the accepted norms of the time?
Certainly. The conditions of 19th century surgery were, to be blunt, nothing short of catastrophic. Surgical knowledge was limited, diagnostic tools were rudimentary, and the mortality rates, well, they were terrifyingly high, even for straightforward procedures.
And the stories about surgeons operating in their street clothes, the unwashed coats, that's all true.
Oh, absolutely. Surgeons would operate in coats, often stiff with blood and dried pus from previous operations. It was worn almost as a badge of honor.
A sign of experience.
Exactly. And instruments were rarely, if ever, sterilized. The whole atmosphere was just conducive to infection. The critical dogma that Lister challenged involved the understanding of pus. Pus formation or suppuration was mistakenly regarded as laudable pus, a normal, even expected part of the body's healing process.
So they thought it was a good sign.
A very good sign, they believed. And this belief led to a complete acceptance of widespread wound sepsis and gangrene, which often necessitated radical amputation just to save the patient. It was a crisis that needed a paradigm shift.
So medical leaders weren't looking outward for the cause of infection. They were seeing it as an inevitable biological process. But Lister found his inspiration elsewhere, didn't he? Not in clinical practice, but in chemistry.
Indeed. From the work of Louis Pasteur in France, Pasteur had famously disproved the theory of spontaneous generation. His germ theory demonstrated that fermentation and putrefaction were caused by minute airborne microbes.
And Lister made the leap.
He made the monumental intellectual leap. If microbes cause decomposition outside the body, they must be the cause of infection and suppuration inside a wound exposed to the air.
Which must have been fiercely resisted.
It completely contradicted centuries of accepted medical belief.
His hypothesis was revolutionary then, but so deceptively simple now. Airborne microorganisms cause wound infection, so he needed a barrier.
Precisely. He sought an antiseptic shield to place between the open wound and the environment. He focused initially on compound fractures, which were notoriously deadly. They almost always required amputation.
The highest stakes testing ground.
Exactly. After exploring several chemicals, he settled on carbolic acid, or phenol. It had been used in sewage systems to disinfect. He began his experiments between 1865 and 1867. A famous early case involved an 11-year-old boy with a compound fracture. Lister applied a dressing soaked in carbolic acid to the exposed bone. 4 days later, he replaced it, and there was no sign of infection. The bones had begun to fuse without that dreaded suppuration.
And the statistical results he published must have been impossible to ignore, even for his detractors.
They were astonishing. From 1865 to 1867, he treated 12 cases of compound fractures. 9 of those remained entirely infection-free. Considering that sepsis was practically guaranteed before, this was an unprecedented reduction in mortality.
Yeah.
It proved infection was preventable.
So the antiseptic method was formalized. It moved beyond just the dressing to the surgical staff themselves.
Yes, the detailed protocol began around 1867. It involved applying carbolic acid lotion directly to the wound, then an antiseptic paste to seal it. But the most profound changes were directed at the surgical team.
This is the real legacy, isn't it? The beginning of sterile technique.
It is. Surgeons were advised to wear clean gloves and to meticulously wash their hands and instruments in a 5% carbolic acid solution. This was a radical departure. He also advised against porous instrument handles made of wood or ivory because they retained microbes.
He was laying the conceptual groundwork for everything we do today. But we should touch on the more controversial period of the carbolic spray, the donkey engine. It illustrates the trial and error involved.
It does. This device was used from 1871 to 1887. Lister genuinely believed the air itself was the primary vector. So he introduced a 1.100 dilution of carbolic acid lotion sprayed via increasingly complex machines, handheld pumps, foot sprays, and eventually the notorious tripod steam spray.
Which sounds quite toxic for everyone in the room.
It was. While it did contribute to huge reductions in mortality, the practice itself was toxic. Patients and staff were constantly exposed, leading to side effects like carboluria, carbolic acid poisoning. Lister eventually abandoned it as he realized direct contact was the main issue, not just airborne transmission.
So, the spray was a flawed but necessary step. The lasting achievement wasn't the chemical itself, but the concept.
Exactly. The legacy is undeniable. Lister introduced germ theory to the operating theater and laid the foundation for antisepsis. Modern practice has refined this into asepsis, the total exclusion of germs. But that entire framework rests upon Lister's initial monumental paradigm shift.
And if Lister's work was the revolution in safety, the next major revolution, which dominates our field today, is about precision and access. I'm talking about minimally invasive surgery, or MIS, and robotics. This transition fundamentally altered the approach from large incisions to working through keyholes. The clinical benefits of MIS are well known, but for our audience, let's focus on the engineering trade-offs. What were the inherent physical limitations of traditional laparoscopy that demanded a robotic solution?
Right. Moving away from open surgery had obvious patient benefits. Shorter recovery, fewer complications, less blood loss. Laparoscopy achieved this, but it created a massive ergonomic and sensory deficit for the surgeon.
A deficit in feedback, both visual and tactile.
Precisely. First, the visual deficit. The camera provided a two-dimensional image. That lack of depth perception makes fine dissection so much harder. Second, the impaired haptic feedback. The long, stiff instruments transferred almost no tactile or force feedback.
So you couldn't feel the tissue.
You couldn't palpate tissue density or stiffness at all. You had to rely entirely on vision, which in 2D was often inadequate.
And crucially, the movement itself was inherently unnatural.
Yes, the fulcrum effect. The fixed access point acts as a fulcrum. When a surgeon moves their hand left outside the body, the instrument tip moves right inside.
It's completely counterintuitive.
Highly non-intuitive. It creates a very steep learning curve. So while laparoscopy reduced patient trauma, it massively amplified the physical and mental demands on the surgeon.
And that is where the robotic solution, specifically telemanipulation, steps in, a classic case of engineering overcoming biological limits.
Absolutely. Robot-assisted surgery means the surgeon controls robotic arms from a master console, and it's designed to resolve those three core limitations. Firstly, it eliminates the fulcrum effect. The instrument tip moves in the same direction as the surgeon's hand,
Making it immediately more intuitive, like open surgery.
Yes. Secondly, it provides 3D visual displays, solving the critical 2D challenge. And perhaps the most impactful advantage is the dexterity. The slave instruments use endo-wrist technology, providing articulation with far more degrees of freedom than the human wrist.
Allowing for complex movements in a very confined space.
Movements that are simply impossible with a straight laparoscopic instrument. It enables faster, more accurate dissection and suturing.
I often hear surgeons comment on the ergonomic improvement. Operating from a console must be a game changer for reducing fatigue.
It's a critical, often understated benefit. Sitting comfortably versus standing for hours reduces fatigue, minimizes physiological tremor, and allows for longer periods of focus.
And the robot holds the ports steady, which means less trauma for the patient.
Directly. Less trauma on the abdominal wall tissues than you might get with human-held instruments.
Looking at the history, the market dominance of the Da Vinci system is indisputable. What was its impact, and how is that landscape changing now?
Well, robot-assisted surgery actually began quite early. The first neurosurgical procedure was in 1985, but the modern era really began in the early 2000s when the Da Vinci system from Intuitive Surgical received FDA approval.
And it became the benchmark.
It did. Its sheer scale over 875,000 procedures in 2013 alone meant that for many years, robotic surgery and Da Vinci were synonymous.
But innovation requires competition, and the market is now rapidly diversifying.
Absolutely. The Da Vinci's dominance is now being challenged by numerous platforms, including Robotics, Titan Medical, and the Versius system. This competition is forcing innovation in critical areas the early models lacked: better portability, lower cost, more haptic feedback, and smaller, more flexible designs.
The next phase is about modularity and accessibility.
Precisely. And before we move on, we should briefly mention Note's natural orifice transluminal endoscopic surgery.
The extreme edge of MIS.
It is accessing the abdominal cavity via natural orifices, eliminating visible scars. The technical demands are immense. Systems have to be incredibly flexible and long and maintain dexterity. In these cases, the fidelity of haptic feedback becomes absolutely essential.
If we contrast the blunt force of Lister's carbolic acid with the precision of modern robotics, the leap is immense. Let's drill down into the enabling technologies, the sensing, actuation, and control systems. Here's where it gets really interesting. Let's start with vision and sensation. We agreed the lack of natural touch was a primary failing of early MIS. How are modern systems incorporating force sensing and advanced imaging to give the surgeon both assistive eyes and a verifiable sense of touch?
The concept of assistive eyes relies on integrating multiple imaging modalities so the surgeon can see beyond the surface layer. Traditional tools like ultrasound, CT, and MRI are no longer just diagnostic. They're now deeply integrated into intraoperative systems.
So ultrasound is still critical.
Oh yes, for its low cost, safety, and real-time imaging beneath the skin. Modern systems like the FlexFocus 800 for laparoscopic use offer high-resolution real-time imaging, which is vital when navigating near-critical structures.
And when we're talking about orthopedics, the spatial resolution of CT and MRI is non-negotiable.
Precisely. CT excels at hard tissue, like bone, the cornerstone of orthopedic planning. MRI excels at soft tissue muscle, cartilage, and is safe for intraoperative use.
And the technological strides in resolution are phenomenal.
They are. The Aquilian Precision CT, for example, can detect anatomy down to 150 microns, using deep learning algorithms to double the resolution. This isn't just a slight improvement, it fundamentally changes the detail available for preoperative templating.
And what about what the surgeon sees in real time on the console? How has endoscopy evolved?
Endoscopy is now a sophisticated visual ecosystem. High-definition cameras are standard, but the real power is in enhanced vision. Narrowband imaging, NBI for instance, uses specific light wavelengths to highlight vascular patterns.
Which improves assessment of things like polyps.
Significantly. And crucially for robotics, newer systems focus on tracking and depth perception. Binocular eye tracking systems now measure soft retinal tissue deformation, attempting to replicate the subtle cues a surgeon uses to judge distance.
So it's the synthesis of all these visual inputs that creates that assistive eye.
Exactly.
Right.
Real-time US, high-res pre-op CT and MRI, and enhanced endoscopy all working together.
Okay, let's return to the sense of touch. The lack of haptic feedback is still a huge clinical problem. What engineering approaches have been most successful in overcoming this?
It is an immense challenge. You can't just put a large sensor in the tip of a fine surgical instrument. We had to break haptics into two manageable problems: kinesthetic and tactile.
Can you break those down for us?
Of course. Kinesthetic haptics refers to the large-scale forces and torques sensed in your joints and muscles. The feedback that tells you a tissue is resistant. That's the most common form in current robots. Tactile haptics involves more subtle feedback, like vibration and pressure, which is increasingly being used in compact wearable systems.
And to get that data, you need highly precise, sterilizable sensors at the instrument tip. Which technology is proving to be the most robust and disruptive in complex surgical channels?
Well, the race has definitely prioritized technologies that are immune to the noisy surgical environment. Established technologies like strain gauges are easily miniaturized, but they are highly susceptible to electromagnetic noise. Capacitive sensors are more stable in wet environments, but require complex signal processing.
So which is the winner in that high-precision, confined space environment?
In terms of disruption, the clear winner, particularly in neurosurgery or endoscopy, is optical sensing, primarily using fiber Bragg gratings or FBG sensors.
Why FBG sensors? What makes them superior?
Because they measure force based on light changes. Critically, this means they work exceptionally well in magnetic environments, which is essential for intraoperative use alongside an MRI. They also exhibit less hysteresis, meaning less lag in their force measurement, and they are highly biocompatible and small. This makes them ideal for detecting the 3D bending and flexible robotic arms or catheters.
They solve the magnetic noise problem?
Precisely. We should also mention piezoelectric sensors, which are unique as they can be used for both the sensing and actuation. They're MRI compatible and often used in precise biopsy probes.
So once the force is measured, how do you translate that data back into something the surgeon can interpret as touch?
This is where we close the loop. For kinesthetic feedback, we use graspable systems at the master console, like the Geomagic Touch. These use motors to transfer force feedback back to a stylus or grip.
So the surgeon literally feels the resistance.
Yes. For tactile feedback, we rely more on wearable mixed systems. For instance, integrating a tactile sensor into a tooltip and providing sensory substitution like a vibration to the surgeon's fingertips.
And this is already in clinical use, particularly in orthopedics.
It is. The Mako tactile guidance system in unicompartmental knee arthroplasty is a prime example. The system uses force feedback not just to inform the surgeon, but to restrict their movement to a predefined safe cutting zone.
So if the tool moves outside the preset boundary, the system physically pushes back.
Exactly. Prevents accidental tissue or bone removal.
That transition from passive sensing to active restriction is a perfect segue into control. The actuators that drive movement must be miniature yet powerful. What methods are proving most effective?
Since large DC motors are unsuitable, actuators are typically installed remotely. Cable-driven actuation is the workhorse used in the Da Vinci. It uses either a cable pulley system for standard laparoscopy or the tendon sheath mechanism. The latter is crucial for flexible endoscopy, where the cable routes inside a flexible tube.
If the tendon sheath mechanism is necessary for flexibility, what's the main engineering challenge it introduces?
The key challenge is backlash hysteresis. Hysteresis is the lag or difference between the force you apply and the resulting motion caused by friction.
So for the surgeon, it feels mushy, a loss of precision.
A loss of immediate responsive control. Engineers are constantly developing algorithms to compensate for that force loss to maintain high fidelity. Beyond cables, we see disruptive technologies. Flexible fluidic actuation uses hydraulic or pneumatic pressure to bend or elongate elastic materials.
Then you have smart materials.
Yes, shape memory alloys, or SMAs, recover their shape when stimulated by heat or magnetic fields. And piezoelectric actuators, whose ultrasonic motors are MRI compatible and ideal for precise probes.
And the most intriguing is magnetic actuation.
It is. This eliminates internal motors or cables. The tool is controlled wirelessly using external magnetic fields, but it suffers from high hysteresis and sensitivity to other metals in the OR.
That brings us to control. The software ensuring all this is stable. How are algorithms addressing the fundamental stability challenges of remote flexible systems?
Safety is paramount. We rely on bilateral control systems for two-way communication. The core problem is communication delay. Even milliseconds of lag can cause instability. Crucially, we use interaction control, which allows the robot to safely interact with soft, unstructured environments. This is split into two philosophies.
Admittance and impedance control.
Exactly. Admittance control prioritizes robustness and safety, but sacrifices some accuracy. Impedance control aims for high positional precision, though that's technically demanding. The choice depends on the task.
And the unique challenge for flexible manipulators is vibration, surely.
Instability and vibration, yes. If the arm flexes too much, the control can become chaotic. We split control techniques into model-based and non-model-based strategies to manage this.
Could you elaborate on how those two differ in solving vibration?
Model-based controls require an accurate mathematical understanding of the system. For instance, input shaping sends anti-vibrational signals to cancel the oscillation before it even occurs. But if the environment changes, the model becomes inaccurate. Non-model-based controllers use real-time sensor feedback. They're more adaptive.
So things like fuzzy logic control or adaptive control?
Exactly. Adaptive control online tunes its parameters to adjust to a changing environment, offering a high degree of robustness. The sophistication of these systems is what turns mechanical parts into an intelligent surgical engine.
These capabilities, hyper-accurate sensing, flexible actuation, sophisticated control, all point inexorably toward the ultimate goal of surgical autonomy. So let's look at the established spectrum. What are the defined levels of automation, and why are orthopedics and neurosurgery so uniquely well-suited for autonomous intervention right now?
Right. Autonomy isn't a binary concept. It's a meticulously defined spectrum. It starts at the lowest level, no autonomy, which is pure teleoperation, like the early Da Vinci systems. It then moves through robotic assistance, up to specific task autonomy, where the robot can execute a pre-programmed task, like tying a suture, under direct supervision.
And the higher levels?
Mid to high level is conditional autonomy, where the robot generates and executes a preoperative plan, and the surgeon provides supervision and the final go-ahead. Then there's high autonomy, where the robot makes real-time decisions during the procedure under doctor oversight. Full autonomy, where the robot works without any human assistance, is still the theoretical endpoint.
Beyond pure technological feasibility, what's the critical rationale driving this push for more automation?
The rationale is compelling and patient-centric. Automation ensures extremely high precision, efficiency, and it eliminates human factors like surgeon tremor and fatigue.
So it's about consistent quality across a high volume of cases.
Exactly. We already see it in action. The Artis hair restoration system performs fully autonomous follicle removal under image guidance.
But orthopedics and neurosurgery have really led the way. Why those fields specifically?
The advantage is purely structural and physical. These fields are best placed for automation because the tissues involved, bone and cranial structures, are non-deformable and stiff.
And that is the critical distinction.
It is. It means surgical tasks like drilling a screw hole or cutting a specific bone geometry can be mapped perfectly during preoperative imaging. Since the anatomy won't shift or move during the procedure, unlike soft tissue, the robot can follow the plan with extreme accuracy and consistency.
So the stiffness of the tissue eliminates the need for complex, real-time, soft tissue deformation algorithms.
Precisely. The key case study is the T-Solution 1 surgical system, used for total hip and knee arthroplasty. This is the textbook example of supervisory controlled automation. The surgeon uses preoperative CT images to plan the bone preparation. The robot then executes the autonomous bone drilling based on that plan. The surgeon plans, supervises, and controls initiation, but the critical precision task is automated.
If that system is so accurate, why is the surgeon still required to supervise? Is the bottleneck technical or regulatory?
It's a fascinating bottleneck that is currently more regulatory and liability-driven than technical. Technically, the system could perform the entire plan perfectly, but regulatory bodies like the FDA demand proof of safety and efficacy equivalent to a human expert.
An incredibly high standard to meet.
It is. So we live in this productive middle ground. The robot handles the precision, but the human retains the critical conditional judgment loop. And this model is also ideal for radiosurgery. Systems like CyberKnife are effectively fully autonomous. They use preoperative scans to plan radiation dosage and real-time tracking to adjust beam delivery.
You also mentioned advances in soft tissue that hint at the future. You use the term positively thigmotactic algorithms. What does thigmotactic mean in the context of autonomous catheter navigation?
That's a great question. It's pure engineering jargon. Thigmotaxis literally means touch response. In the context of autonomous cardiovascular surgery, it means the algorithm allows the catheter to positively seek and follow a surface like a tissue wall inside the heart while maintaining a constant low contact force.
So it prevents the catheter from floating aimlessly or causing damage.
Exactly. And it's often paired with haptic vision, which uses machine learning to interpret visual cues as force cues, creating a hybrid touch sensing capability that enables autonomous navigation within heart chambers.
That provides a superb analysis of the transformation in the operating theater. Now let's pivot entirely to the end product for orthopedic patients' prostheses. Let's trace the history from the craft-based model of Industry 1.0 to the digital infrastructure of Industry 3.0. What were the major shifts that elevated prosthetics from an ad hoc craft to a structured, professional specialization?
The evolution is stark. In Industry 1.0, production was strictly craft-based. Devices were made by local craftspeople cobblers, metalworkers using wood, leather, and rudimentary metal.
So design advancement was minimal for centuries.
Very minimal. And devices were often unaffordable and poorly fitted. Industry 2.0 provided the crucial inflection point, largely driven by large-scale conflict. The American Civil War left tens of thousands of amputees. The subsequent Great Civil War benefaction provided federal funding for prostheses for veterans. This economic driver generated a rapid burst of patented designs and critically established dedicated prosthetic workshops.
Creating the first recognized standalone trade.
Precisely. It moved the practice away from general craft to a specialized profession.
So government funding and mass casualties created the specialization. What was the impact of World War I in pushing this toward true industrialization?
World War I cemented the industrial approach. The sheer volume of casualties spurred the development of modular prosthetic systems. Otto Bach in Germany pioneered this. They focused on using standardized, mass-produced, and quality-tested components: knees, pylons, feet. Everything became factory-tested and replaceable.
Except for the socket.
Except for the socket, which remained handcrafted. This modularity significantly improved efficiency and safety. Concurrently, we saw essential external technologies being laid. Early research into myoelectric control began during WWII, and the post-war revolution in chemical sciences gave us synthetic polymers.
Which led to laminated sockets replacing carved wood.
Yes, in the 1960s, paving the way for the digital era.
Industry 3.0 then marked the shift from experience-based trade secrets to objectively evaluated design. How did digital tools formalize that evidence-based approach?
The period from the 1950s to the 2010s saw prosthetic design move firmly into the realm of interdisciplinary engineering. Academic developments were pivotal, like the patellar tendon bearing socket, which were objectively studied based on gait analysis.
And in production, digitization began with CAD/CAM in the 80s.
It did. Systems like Can-Hi-Fi and Seattle ShapeMaker allowed prosthetists to scan the residual limb, digitize the shape, and modify the socket design on a screen, adding efficiency and reproducible accuracy.
But for the patient, the most significant change was the introduction of intelligence into the components themselves.
Undeniably. The advent of microprocessor control, or MPC, in components was the most visible functional impact. MPC knees, like the C-Leg in 1997, incorporated digital sensors to dynamically adjust resistance based on walking phase, profoundly changing function, stability, and safety.
This era also forced a necessary but painful transformation in clinical practice, the requirement for objective outcome measures.
This was a pivotal external pressure point. Clinicians had long relied on subjective experience. I know what works best for this patient. But as costs escalated, payers demanded justification.
The watershed moment was the Levinson Report in 2011.
It was. It was highly critical of the subjective nature of prosthetic billing. It forced insurers to mandate the use of objective, measurable outcome criteria to justify reimbursement.
So, evidence-based, data-driven practice became the daily clinical reality.
It was cemented into the daily reality, yes.
That sets the stage. We now enter Industry 4.0, defined by the convergence of physical, digital, and biological systems. What specific breakthroughs are defining the sector now?
Industry 4.0 is characterized by the creation of smart, or cyber-physical prostheses. It's an era where 3D printing, the Internet of Things, machine learning, and big data converge. The first area of revolution is the socket, the perennial challenge of fit, comfort, and volume fluctuation.
So we're moving beyond just adding or removing stump socks.
Far beyond. New approaches include manually adjustable sockets using materials from high-performance sports. But the real disruption is automating that adjustment.
Using machine learning.
Absolutely. The future lies in fully automated adjustable sockets generated by ML. Vast databases of anthropometric and biomechanical data are captured by advanced imaging, even smartphone apps, coupled with embedded sensors. ML algorithms then generate the optimal custom socket geometry, and 3D printing makes this mass customization economically viable.
Which has profound implications for the professional's role.
It does. The prosthetist is transitioning from being a hands-on craftsperson to becoming a clinical technology manager responsible for data analysis and system integration.
This digital convergence also extends into wearables, into the idea of smart garment.
Yes, new fibers and sensors are integrated into liners, turning the socket liner itself into an active sensor platform. These smart sockets monitor pressure and temperature, streaming data via IoT.
Allowing the components to respond dynamically to the amputee's state.
Exactly, enhancing stability and natural movement.
And finally, the ultimate hybrid solution, which bridges the gap between the device and biology, osseointegration.
Osseointegration, or OI, is the pinnacle of this convergence. It attaches the prosthetic directly to a bone-anchored implant, completely eliminating the socket interface. This vastly improves biomechanics, stability, and crucially osseoperception, the ability to feel the ground through direct bone conduction.
There are risks, of course. Infection, loosening.
There are genuine risks, but international experience confirms its increasing viability. It is the future for suitable patients. We must also address the powerful disruptive force of customer empowerment in Industry 4.0. Social media has radically shifted the power dynamic.
So amputees can connect directly with engineers and designers, bypassing the traditional clinical filter.
They can, and this has led to innovation focused on aesthetics and personalization, which was entirely missing from the clinical model.
You see this with fairings, the personalized add-ons?
Exactly. Produced via 3D printing, they allow the amputee to express their identity. And at the other end, accessibility is being driven by technology. Open-source 3D printed hands have shown a massive unmet need for affordable solutions. The improved quality of 3D printing, combined with global smartphone access and telemedicine, promises to increase equitable access to care. This trend is set to fundamentally disrupt current business models. If we connect these two threads, surgical robotics and advanced prosthetics, to the bigger picture, both are clearly moving towards sophisticated, supervised autonomy. The core challenges remain stubbornly consistent across both sectors: achieving technological maturity, managing the high cost of implementation and upgrades, and navigating rigorous regulatory hurdles.
And the ethical and legal responsibility if something goes wrong.
Crucially, we must establish clear responsibility if a mechanical or software failure occurs. So for the foreseeable future, supervised autonomy seems to be the most viable and ethically sound level of implementation. This is the model where human expertise provides the critical, nuanced judgment, while advanced technologies perform the highly precise, repetitive, and fatiguing tasks.
And the message for the medical professional is to proactively navigate these changes.
Yes, the future of care requires moving away from subjective, hands-on craft models towards evidence-based, data-driven technology management. This is the only way to ensure the human component remains the critical decision maker.
That was a phenomenal deep dive. We have charted the evolution from Joseph Lister's use of carbolic acid in 1865 to the current challenges of managing patient data for machine learning models and prosthetics. The evolution of orthopedic care is accelerating exponentially. If you found this deep dive valuable, please take a moment to rate and share the show with your colleagues. Finally, a provocative thought to leave you with. Considering the successful application of automated bone drilling in orthopedics using systems like the T-Solution 1 and the rapid advances in AI that allow preoperative plan execution in a stiff, predictable environment, how long before the current standard of care for a procedure like total knee replacement moves entirely from assisted surgery to conditional autonomy, where the surgeon's primary role is risk management, supervision, and authorization? Thank you for joining us for this deep dive into the future of precision. We'll see you next time.